Hello, and welcome back to the Calculus 1 playlist. In today's video, we're going to be talking about logarithmic and exponential functions. So to start, we'll be looking at what an exponential function is and kind of what it looks like. Then we'll be moving on to the logarithmic functions and see how they relate to exponential functions. And finally, we'll touch on some natural logarithms before going over some examples. So without further ado, let's begin. So what is an exponential function? Well, it turns out an exponential function is just a function that takes up the form f of x is equal to a raised to x. Great. If you recall, in our functions video, we defined a different function known as the power function, which looks like this, x raised to a. So these are different. This one is the power, and this is the exponential. So the exponential value has the independent variable of x as the, in the exponent, whereas the power function has some constant as the exponent. So that's the difference between them. So graphically speaking, how would we represent a exponential function? Well, it turns out that this function right here, a of x, it has a different type of domain and range to the functions we've looked at recently. So I'll draw it out on the graph first. But this is kind of the form that an exponential function takes. So the domain of this function, as you can tell, goes from negative infinity to infinity. We can have any x value. We can choose our x value variable to be of any value. But our range, our output, is specified between 0 to infinity, where 0 is not included. Now, this is really interesting. So I'll this f of x is equal to a raised to x. Now, this is really interesting. It has some cool properties together. So to start, let's look at defining some of these rules that go with the exponential functions. So we have ax plus y is just equal to ax and ay. We have ax minus y is equal to ax over ay. Then we have ax, and that's all raised to y, is equal to axy. And last but not least, we have bx is equal to ax and bx. Great. It's really cool. And one thing to note is when a is equivalent to 0, what is the value? So when we have a is equal to 0, when x is equal to 0, so when our input value, let's say this is x and this is f of x, so when x is equal to 0, well, it turns out that this value is 1, which is a unique property of exponential functions. Well, if you ask why that is, so if we want to know why this works, if we kind of just write out a few terms of an exponential function, we'll be able to see what it's talking about. So let's say we have, I'll do a few, x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3. I think that should be enough to prove my case. And let's use a base of 2. I think, say a is equal to 2 for all of them. Well, it turns out if we have 2 raised to 0, we have 2 raised to 1, 2 raised to 2, and 2 raised to 3. We know the value for all of these, right? We want to find out what 2 raised to 0 is. Well, it turns out that this is 8, this is 4, this is 2, and we don't know what this value is. Well, it turns out what we're doing is we're taking 2 raised to x, since our base of a is equal to 2, and we're doing this 2 times 2 times 2 times 2 x amount of times. So subsequently, that means we're multiplying by 2 at each interval or each level of x that we're adding on. So between here to here, we multiply by 2. Between here to here, we multiply by 2. And we could say then that from here to here, we multiply by 2. And you can see that this is holding true for these cases. As well, you can say if we're going back, and I'll switch colors, we're dividing by 2, then we're dividing by 2, and subsequently we'd have to divide by 2. Great, so when we're looking at a number that when you have 2 and you divide by 2, the only number that's possible is 1. And subsequently, when you have 1, the only number that multiplies by 2 to get 2 is 2. which makes sense. So we know that a neat property of exponentials is that a of 0 is equal to 1 for any a, for all a. Great. So let's move on. What is the inverse of an exponential function? What does this look like? And recall, we talked about inverses in the previous videos. We talked about an inverse function and an inverse trig function. An inverse function is just the function that is reflected across y is equal to x, right? So it turns out that the inverse function of an exponential function is the logarithmic function. Perfect, that's really neat. So what does this look like? Well, we could say then that if we have y is equal to a of x, this is our regular exponential function, then if we take the inverse, I'll put inverse, well, it turns out that's represented as the following: log base a, and we have y, and that is all equal to x. So this is the inverse function. And so let me write some things about the notation right here. This value is known as the base. That is the base, so that corresponds to here. And this is the exponent that we're looking for, and y value is our dependent variable. So graphically, what does this look like? So we know that an exponential function kind of looks like this. Well, we know that inverse functions are reflected about the line y is equal to x. Y is equal to x. So if we're reflecting this function about y is equal to x, well, it turns out this is what our logarithmic function looks like. So this is y is equal to log base a of x, or log base. This is our function log base a y, and this is our function y is equal to a raised to x. Great. So an interesting property, if you recall, from inverse functions is the cancellation formula. So if we have f of -1 of x, that should just equal to x. And also, if we have f of f of x, the inverse, that should also give x. This is known as the cancellation formulas. Therefore, for logarithmic functions, we can say that if we have log base a, and we have a raised to x here, we can say that that equals to x. As well, if we have a log with a base of a and x, we can say that that is equal to x. So this is a neat property derived from the cancellation formulas of inverse functions. So that is definitely something to note. Perfect. So now if we want to look at the domain and range of log, well, we know it's the inverse of exponential functions. So the domain then becomes the range of the previous, which is 0 to infinity. And the range varies from -infinity to infinity, which you could gauge from the graph. Perfect. And now some neat rules with logarithms, and I'll move this down so we have a bit more room. If we have, let's say, log base a, and we have x of y, this is just equal to log a x plus log a y. And if we have log base a x divided by y, this is equal to log a x minus log a y. Perfect. And last but not least, we have log base a, and we'll have x here, and this is raised to b. Well, this just happens to be b log a x. So these are some important rules of logarithms, and this b value, b is an element of all the real numbers. So let's look at an example quickly. So for the first example, we've got, let's say, 7 raised to 5 is equal to 16805. Convert to logarithmic form. So we have that this function in the form ax is equal to y. We need to convert it to the form log a y is equal to x. So it's pretty straightforward. We'd have log base 7, 16805, and that should all equal to 5. Pretty straightforward. I will say it's a very easy example to start. Second example, we'll have 3 individual parts to this. So first, simplify these functions. So we'll have I, and we're going to have log of base 5, 125. So let's simplify this to its exact value. So what we can do straight away is we can break this down to log 5, and we go 5 raised to 3. And recall from this law right here, we can convert that to this form. Meaning we can bring down the 3, so we'd have 3 log 5 raised to 5, or to 5. Perfect. Well, it turns out that this is just 1. Log of base 5 with 5 is 1. How do we know this? Again, that's with right here. Let's find the inverse law, the cancellation formula right here. So if we have something in the following form, a logarithmic function in the following form, we can say that this right here, if we have this form, log base a to a. So we can say that all of this is just equal to 3. Cool. So for the second example, we have log with base 1/4 to 16. Well, what can we do in this case? Again, we want to have it in a form such that we're able to get rid of this logarithmic term in this case. Well, it turns out if we look at 16, 16 is equal to 1/4 if we bring it to the top and then we square it, right? Because if we bring it to the top, we have 1/4 to negative 2 is equal to 4 squared, which is equal to 16. So we can say we can put 16 into this form. So, well, it turns out we can go log 1/4, not 14. Sorry, we'll have log 1/4 raised to, or to 1/4 raised to negative 2. We can bring down negative 2, have it in this form, and as previous, this is just equal to 1. So we have our solution. All of this simplifies to negative 2. Great. And for the last part of this example, we'll have log of base 2 to 1/8. Well, again, we want to have 1/8 and base 2, so we want our 2 to be related somehow. So we can say 1/8. Well, it turns out 1/8, well, 2 cubed is equal to 8, but 2 negative 3 is equal to 1/8. So we can say that, then we have log base 2 with 2 to negative 3. Bring down the negative 3. Log base 2 of 2. Well, again, this goes to 1, so our solution is negative 3. Again, very straightforward, just using the laws of logarithms to our advantage. And then the last but not least example, we want to combine log terms. So we're going to have this problem, 1/4 log a minus 8 log b plus 2. And note, if we just have a log like this and there's no base here, like we don't have a base value like we did in this case where we have base 2, this is just actually log base 10. So we kind of assume everything is base 10. That's kind of how our counting system works. It's a base 10 system. So we assume everything is of log base 10 if there's no other base given. So this just means log base 10. But anyways, using the laws of logarithms, let's first go ahead and bring 1/4 to the top. As you can see from the third law again. If we have something in front, we can bring it to the top into this form. So we can go like that and do the same for the second logarithm. So b plus 2 gets raised to the 8. And now using the second law of logarithms, we can take this subtracting logarithms of the same base and put them into one logarithm where everything is being divided. So we have log of a raised to 1 over 4 all over b plus 2 to 8. And now everything is combined into like terms. Perfect. Great, so now let's talk about our discussion on natural logarithms. Let's write that down, natural logarithms. And before we do that, we need to define something called Euler's number. Euler's number. Well, Euler was a famous mathematician back in the day, and he had a constant named after him, and it was found by bankers who found this relationship with a specific number, and the number is represented as E, Euler's number, which is equal to approximately 2.72. And it goes on and on and on. But essentially, I'm not going to go into a derivation of how it was found, but essentially it came from the idea of principal interest. So you can look at a formal definition, but it will actually be something, I guess we'll be relating to it. It comes from calculus. It turns out if you take the limit, which you'll learn how to do eventually, actually after this next section of the course, of 1 plus 1 over n, so the limit of n as n approaches infinity, raised to n, it turns out that you get this number, E. You get this number, Euler's constant. And this is a really important number for economists, and principal interest, mortgage rates, a whole bunch of different mathematical topics. So as you increase the number n, the value of that function gets closer to, tends towards infinity. This is something we'll cover more thoroughly inside of limits part of the calculus course. But overall, just to know that that's what Euler's number is, and if you're curious more about how it's derived, you can look into that. Well, it turns out a logarithm, so a logarithm with base e is called a natural logarithm. So it's denoted as log base e, and let's put this y is equal to x. Well, we kind of just refer it to as ln. We say ln of y is equal to x. We don't need to put it as log base e, but essentially that's the notation for it. So we can say that ln x is equal to y. I guess I'm switching the notation for this one. I'll be consistent. I'll go like this. We can say then that the inverse is e raised to y is equal to x, if we want to be specific. And then based off the cancellation formulas, we have the following rules. We have ln e raised to x is equal to x, because again, we're having a log base of e with the argument being e. That gives you 1 if you have it in this form, right? So if we have like this, we can just say that that is equal to 1. And again, conversely, we have e raised to ln of x is just equal to x as well. So again, let's say x is equal to 1 in this case. So if we have e ln 1, well, that's just equal to 1. Great. So apart from this, the rules of natural logarithms, it turns out that they follow the exact same rules as the logarithms. And since a logarithm is a special case of a logarithm, it's just the base of Euler's number. So we're going to talk about the domain and range quickly, just define it again. But domain, as you'd expect, goes from 0 to infinity, plus the range tends from negative infinity to infinity. And then graphically speaking, we have it looking like this. Perfect. And so some key points to recognize on this graph is that at right here and right here, what are our values of the logarithm function? Well, it turns out that ln, when we have x, and this is y, and let's say that this is f of x is equal to ln x. Well, it turns out that this point is x is equal to 1. So at x is equal to 1, our function value, so f of 1 is equal to 0. So ln of x is equal to 0. And in this case, when we have x is equal to e, we have ln of, again, as you'd expect, this is ln e. E is equal to 1. So f of 1 is equal to, or f of e, sorry, f of e is equal to 1. And I guess I'll draw out the exponential form for it for you guys. That is y is equal to ln of x, or sorry, e raised to x. Perfect. So moving on, we can go through some example problems quickly. And again, not too difficult. We've probably already touched on the harder example problems when I tried to drill through the laws of logarithms. But if we have ln of x, and let's say that that is equal to 4, if we want to convert that to exponential form, well, it turns out that that's just x is equal to e raised to 4, because the base right here of a logarithm of a ln is e. So we have e raised to 4 is equal to x. And to highlight again, we have a domain of going from 0 to infinity and negative infinity to infinity, just to highlight quickly the ln of logarithm. So let's go through another example. Right here, we're going to have e raised to 10 minus 4x, and that's going to equal to 10. And let's solve for x. Great. How can we go about doing this? Well, just like you can multiply or divide everything by one side, you can apply a logarithm to both sides for any function. So what we can do here in this case is apply a natural logarithm to 10 minus 4x to both sides. Well, then, using the laws of logarithms, we can bring down this 10 minus 4x to the bottom here. We can go 10 minus 4x ln of e equals to ln 10. Well, we know ln of e is just equal to 1, so we can cancel that as a 1. So now we have 10 minus 4x is equal to ln 10, and just by using simple algebra, we can do 10 plus ln 10 is equal to 4x. And finally, we can say, minus ln 10. So it's simple algebra, but I got it wrong. Minus ln 10. And we divide by everything by 4. We get 1 over 4, 10 minus ln 10 is equal to x. We can actually simplify this a bit. We can go 10 over 4 minus 1 over 4 ln 10 is equal to x. And then if we want, so making this 5 over 2 minus ln 10 raised to 1 over 4. And we can say that this is our solution. Perfect. So not too bad. And overall, to follow very similar rules to logarithms, because the natural logarithm is just a special case of a logarithm where we have the base of e. So another topic I want to touch on quickly is just how to change base of logs. This is not super important. However, you might need to ever change a log in an example. So let's say we have log base b, and we have x as this argument. Then we can say if we want a different base, log base k, of our arguments, we just go like this, and we log base k of our base, and that's it. It's really not too hard, but again, it's just important to know. So let's go through an example of change of base, and I'm not going to spend too much time on it because we're probably not going to face many problems like this, but just something to know, a property of log bases. So we have log base 5 of 10, and we want to change this to a base of 10. Well, we have log base 5 of 10, and that equals to, using our above formula, we have log base 10 of 10 all over log base 10 of 5. Well, this guy cancels, turns out to be 1. So we get 1 over log base 10 of 5, and that's our solution. Perfect. So again, not too hard. And if I want to be nicer with the notation, we can say just 1 over log 5, because as I said previously, base 10 is the assumed base, so we don't need to write down the base of 10. And finally, let's just do a graph of a logarithmic function before we end off the video. This graph f of x is equal to ln of x plus 2 minus 3. So to start, what I like to do is draw the original function. So we're going to draw f of x is equal to ln of x. That's what we're going to first draw. And if you recall, that looks like something like this. And we said that at this value, we have x is equal to 1, and at this value, x is equal to e. And when x is equal to e, the y value, the function value, is equal to 1. Well, then if we shift this by a value of x plus 2, this means we're shifting the function to the left. We'll go ln of x plus 2. We're going to shift by 2 indices. So we're going to have this function value being right here. So we'll have it looking something like this. Let's make it look better. We're going to have our function looking like this. And now our asymptote as well. All our values get shifted to the left by two values. So our value of 0 now occurs at x is equal to -1. And our asymptote is at, this is x is equal to -2. An asymptote is just a value where the function never touches but approaches. So it was 0 previously, now it's -2. And then last but not least, we're just going to shift down by -3. So f of x, and we'll say ln of x plus 2 minus 3, and we'll put that one in the yellow. So all this is we're shifting our function values down 3. So the horizontal asymptote doesn't change, but this value will go down 3. So let's go 1, 2, 3. Let's call this here. And we'll have our function looking something like this. So not the neatest of graphs, but I think you guys get the point. This is x is equal to -1, but the y value drops to y is equal to -3. So no longer 0, it's -3. And you can kind of graph this out on your own, take a look, but overall, very straightforward. If we want to talk about the domain and range for this type of function, I think that would be pretty cool to talk about. You could then say, again, the domain for these values now gets shifted 2 to the left. So you can have any value between up to and not including -2 to infinity and any range. So domain for this function would be -2 to infinity, and range would be -infinity to infinity. And this is our solution. So there you have it. We talked about exponential functions, we talked about logarithms, and we did some examples using natural logarithms as well. So if you enjoyed, please stay tuned to give a like, share, subscribe. And in the next video, we're going to be wrapping up our pre-calculus topic with some examples, just some pre-calculus wrap up before we start our actual calculus. Take care.